So we've talked about the law of refraction, and now we want to apply that to lenses in the same way that we applied the law of reflection to mirrors. So we talked about the law of refraction, um, and refraction um, is the process that makes a lens work. So if we look at the lens over here, um, it's a transparent object and it's shaped in a particular way, right? That it changes that normal um, vector here, right? So you have a lens or a ray that's coming in here, and because of the shape of the lens, it's no longer coming in straight into the lens, and so it's going to refract. And so we can define our lens or design our lens so that it refracts in the way that we want it to. A converging lens, which is what this guy over here is, directs light to a focal point that's on the other side of the lens. So we have rays here, and they all go towards this focal point F. Our distance here is our focal length, just like with a mirror. And in fact, if we look at the refraction, this isn't quite right because it's going to refract over here as well, right? So we can actually, if we analyze this, we can see that it's refracting once when it enters the material and it's refracting a second time when it's leaving the material. And in both cases, you're going to have coefficient of refraction on the inside that's larger than in the air, right? So that angle here, this theta, is going to be smaller because it's going to be closer to perpendicular here. And this angle is going to be smaller than this one. And it causes that ray to move towards the focal point. A diverging lens acts, not surprisingly, in the exact opposite way, right? So you have rays that come in here and they diverge away. So where's the focal length with a diverging lens? It's right here. It's a virtual focal point. And the focal length is negative because it's in front of the lens here. The power of a lens is defined by this focal length. And again, we can think of that, the more powerful a lens is, the more it's going to bend our rays. Okay, so here you can see that it's inversely proportional to that focal length. So let's say my focal length was right here. In order to do that, this would have to bend that ray even more. So it was going up like this. So if I had a focal point here, I would have a more powerful lens. If I had a focal length here, that would mean that my ray coming out of the lens was going like this. In other words, it hadn't bent nearly as much. And so power is a representation of how much your lens is going to bend that light ray. Again, this is negative for a diverging lens because that F is negative because the F is in front of the lens. And notice the units here, and that's a unit that if you were, going to prescribe eyeglasses, this is what you would, your prescription would be in diopters. So we want to have a couple of rules about how rays go through lenses. And these look a lot like the rules that we have for mirrors. Okay, so if we look at our image over here, parallel rays from a distant source, so all our rays 1, 2, and 3 are coming in parallel, converge on a focal point. So anytime a parallel ray comes in here, it's going to hit that focal point. Diverging rays, like this one, are going, if the source is at the focal point, any ray coming from the focal point is going to end up parallel on the other side. So that's the flip side. These two rules are really the same thing. They're just the direction of the ray is changing. And then that gives us our ray tracing rules. So this is that first one. Okay, a ray approaching the lens parallel to the axis, like number 1 here, goes through the far focal point. or appears to come from the from the near focal point, right? So if um, in this case our ray is coming in like this, it appears to come from that focal point. A ray going through the center doesn't refract. Why is that? Well, because your ray is coming in perfectly normal to the surface, right? Because at that point, the surface is like this, and so any ray hitting there in a parallel way is just going to keep going straight. And then again, a ray approaching through a near focal point will emerge as parallel, or in this case, approaching that far focal point. So key point here is if it's coming in parallel, it's going to hit a focal point. If it's coming from the focal point, it's going to leave parallel, and if it hits the center, it's going to go through the lens without changing. Okay, so lenses, a lot of this is, very similar to what we do with mirrors. There are some things that lenses can do that mirrors can't do, but a lot of it is repeating what we've done before. So lenses, like mirrors, form images that can be real or virtual. The image for a camera lens is real. So when we have a converging lens like this and you're outside the focal point, then any ray leaving the top of this lady's head is going to end up meeting at the same point. And that's where we say the image is formed. And in a camera, that's important because we want an image to be formed on the film in the old days that matches what was happening on the outside, right? So if we put that film right here, you'd get a really blurry image because the rays from different parts of this woman would be hitting the same piece of film. But in this instance, every ray from this part hits here. Every ray from her feet hits here. And that's what makes that in focus. The image for a converging lens is real. The image for a diverging lens is virtual. Actually, this is not always true. We'll get to that in a second. The equations for lenses are the same as for mirrors. Okay, so this is the distance of the object from the lens. This is the distance of the image from the lens. And this is the focal point. Now note, these can be negative, right? This guy can be negative if our image is in front of the camera. This one can be negative if our focal length is negative, if we have a diverging lens. And then we can talk about the magnification of our lens, right? So the definition of that magnification is what is the relative size of the object compared to the image? But we can define what that magnification is by the distance of the image and the object.